Okay, very good morning to all of you. We will continue with our discussion on stationarity and also draw conclusions on it. And today we will also discuss the notion of ergodicity a bit more in detail. We have talked about it before, but first let us talk about stationarity. And if you recall, the reason we are looking at this condition of stationarity is, practically speaking, the model that we develop from a finite set of observations collected over a period of time should be usable at some other time as well, right. So, we are requiring that the process satisfy this. Of course, in reality processes may not satisfy this, then we will have to find remedies for that, and we will briefly talk about some non-stationary processes as well today. So, let us recap what strict stationarity is about. Essentially, the joint distribution or the joint PDF of this n observations that we have collected should not change with time, and this is regardless of how many observations you have. So, in the strictest sense, every observation should fall out of the same distribution. That is what stationarity means. There is one point that I want to talk about notation here. Of course, we are using x, as I have said, we will shift over to v shortly, but apart from that, strictly speaking, what is happening is here you have a random signal. So, it is at kth instant, the observation is xk. At k minus 1th instant we have xk minus 1, and at k plus 1 we have xk plus 1, and so on. Now, what I have written on the slide, in the sense the notation that I have used in describing a strict stationarity, is with some abuse of notation. What I mean by that is, the notation xk denotes the observation. Strictly speaking, we should associate with this a random variable, for example, uppercase x subscript k, uppercase x subscript xk k plus 1, and likewise here x subscript k minus 1, and so on. So, the xk for us generally denotes the observation or the value that the signal takes at the kth instant, and associated with this kth observation is this random variable. Remember, we do distinguish between the random variable and the outcome that the random variable takes. Therefore, what you see on the slide in the form of definition of strict stationarity should have been strictly written as f of x1 x2 comma up to xn, or you can say x k1 k2, whichever way you want to look at it, kn should be identical to f of x k1 plus time t comma x subscript k1 k2 plus time t up to x kn plus time t. In other words, the PDF should have been written in terms of the random variables rather than the observations that I have written there, but I will introduce this notation a bit later, and we will revert back to the notation that we are seeing on the slide just for the sake of convenience. In other words, at some point in time you should be able to see xk as an observation, xk as also, that is this xk as an observation and also as a random variable, and sometimes as a random process. Depending on the context, you should be able to interpret it. If there is an ambiguity, of course, I will clarify the same. All right. So, that was the part on the notation. Now, obviously, any process here, coming back to the discussion, any process that is not strictly stationary is said to be non-stationary, pretty much like what we have in a linear world. We define what is linearity, and we say whatever process or system does not obey, whichever system does not obey the linearity definition is said to be non-linear. So, in reality, are all processes, is there any process that is strictly stationary? The answer is most probably no. It is very rare to encounter a situation. In fact, in principle you can't say that any process is strictly stationary. For example, you take a die and generate a random signal by keeping on throwing the die and recording the face value. So, that is the random signal that you generate. Let us say I look at this random process. Now, is it strictly stationary? Can I say it is strictly stationary? If yes, then under what assumptions? What do you think? So, I am just throwing a die and I am recording the face value. This is the random process, the process of throwing a die repeatedly. What do you think?
The die should be unbiased.
Okay, what does it mean on the die physically? What does it mean by unbiased?
The probability of each phase would be equal and
Okay. So, you say you mean to say under those conditions we can assume it to be strictly stationary. Okay. Any other answer?
should be under same conditions.
Sorry?
The experiment should be conducted under same conditions.
Under same conditions. What does same condition mean?
The surface should be same, the throwing angle should be same.
Correct, exactly. So, everything kept the same. The surface should be the same, the throwing angle should be the same, the force should be the same, the die should not undergo deformation. But can we say that? It is not really possible. So, I mean we can't guarantee that the angle would be the same. The surface probably it is the same, but if you look at it at a nano scale, probably the die would undergo some minuscule deformation, the surface probably changes its morphology and so on. So, as you zoom in and zoom in and zoom in, then the process is not stationary. But this kind of idealism is good, is necessary, so that we know theoretically the rigid framework in which we are operating. The hope is that small deviations from this will not cause too much harm to the theory. That is the hope. And what is small, what is large is kind of subjective in some sense, but there are also statistical ways of saying what is not strictly stationary and what is stationary and so on, and we will learn that as we move along, all right. So, there is theory and then there is practice, and one has to be able to appreciate both the theory and the practicing part of it, where we will not satisfy the theory, but it is okay in the sense there are always going to be practical aspects. All right. So, let us look at a simple example of a non-stationary process before we move along. We will talk about, we will return to the stationarity part, but just to get a feel of what is a non-stationary process. We have looked at this signal before. If you recall, when we were computing expectations, we had taken up this example, but there is a slight difference between the conditions in that example and now. The signal is given on the slide, xk, it is a periodic signal, xk is a cosine omega k plus phi. A is amplitude, omega is the frequency, this is a discrete time cosine and phi is the phase or the phase shift, and the randomness in xk comes about due to the randomness in the phase phi, which is uniformly distributed in the interval 0 pi, all right. Now, what do you think is the mean of the signal? Can you calculate the expected value of xk? The purpose of calculating this expectation is to see even if the at least if the expectation is invariant with time. If it is not, then we can straight away conclude that the process is non-stationary. Generally it is very hard to check for non-stationarity, but we can perform some basic calculations such as on mean, computing the mean, variance and so on, and if we somehow chance upon finding that the mean or the variance or later on autocovariance that we introduce will change with time, then we can straight away say that the process is non-stationary. So, as a first step, let us compute the expectation of xk. We have already gone through this calculation, the only difference is now the interval over which the phi is distributed. I will give you a minute to calculate the expectation. Go ahead. You are given, right, that phi is uniformly distributed. Anybody with an answer from the other hall? Anybody has any difficulty in computing expectation? Sorry?
A sin omega t.
Sure? Already now 4 answers have come out. So, which one is the correct one? Shall we go by majority? Please check your answer once again and give me the correct one. Any answer from 241? You're okay? You have some difficulty computing the expectation? You don't want to expect anything. Done. You have the answer. What's the answer?
Minus 2a by pi sin omega.
Okay. Minus 2a by pi sin omega k. Okay. Anybody with the same answer? Okay, good. So, we will go by the Lok Sabha route. Because this is math, you do not need Lok Sabha route. So, that is the answer, right? That is correct. So, minus 2a by pi sin omega k, very good. Now, obviously, here we the mean is a function of time, correct. That means, at any time k, that is as I move across time, when I say time here the sampling instant k, the mean is going to change, and that is a sign of non-stationarity. So, straight away we can conclude that this process or or this signal is non-stationary. In the example previously that we had looked at when we were computing expectations, we had a slightly different interval, if you remember, right. We had the interval between minus pi and pi, am I right. So, there of course, the mean turned out to be 0, but that does not mean that the process is stationary. It is just that in other words, if the the phase here was distributed uniformly in the interval minus pi to pi, we would get the mean to be 0, which is invariant with time. That does not mean that the process is stationary, it only means that it is stationary in mean, we say it is mean stationary. The variance could be changing with time, or any other moment could be changing with time. So, as you can see, it is not easy in practice to verify non-stationarity. Even by hand it is difficult, and from data it is going to be even more difficult. Why? Because the data that we have will be only a single realization. At least by hand we are able to compute across all realizations, but when it comes to verifying stationarity in practice, it is going to be even more difficult, because we will be working only with a single realization. Is that clear? Therefore, when you look at the literature on tests for non-stationarity, there is no test out there which will universally test for all kinds of non-stationarities. One has to specify a priori what non-stationarity one is hypothesizing, and then conduct the test. For that we need to know what are the different kinds of non-stationarities that exist, but we will come to that shortly. But this is something to keep in mind when you are looking out for tests for non-stationarities. You should be first clear what is the null hypothesis in such a test, whether it is assuming there is a linear trend, whether it is assuming the non-stationarity is of integrating type like random walk type, or quadratic trend, or a mix of both. So, there are a few different tests. Be very clear on what the test is actually testing for before you use the non-stationarity test. Many applications will generate non-stationary random signals. Okay. Any questions on this example? Fine. Now, what we do is we take this strict stationarity and come up with a slightly, is not exactly diluted, but slightly different version of stationarity. It is definitely a relaxed version of the strict stationarity that we had seen, and we will see even more relaxed versions. This is not the one that we are going to work with, but for completeness sake let us understand this kind of relaxation or dilution of the strict stationarity definition. This is stationarity is called order stationarity in distribution. Very soon we will talk about order stationarity in moments, where we will talk about stationarity in the second moment, stationarity in the first moment and so on. But this is order stationarity in distribution. What do we mean by order here? It is the number of observations that you are looking at jointly. Essentially you apply the same definition of strict stationarity, but not for any n particularly, for only for a specified n. If you compare with the definition we had here, the strict stationarity demands that the distribution hold for all sets of observations, that all sample sizes that you are looking at, whereas order stationarity is looking at specified user specified value of n. When the distributions are identical, earlier you saw the statement in terms of PDFs, now you are looking at statement in terms of CDFs, that is the only difference. Okay. Why do we bring in CDF? So as to handle discrete valued random processes as well. PDFs are fine or valid for continuous valued random processes, but CDFs are valid for both. Therefore, it is a slightly general version, and you see the notation is now more appropriate, I would say, and it uses this notation that I have talked about earlier. So, the joint random process is said to be nth order stationary in distribution when the distribution of this n observations that you are collectively looking at remains invariant with time. It is a very simple definition. As special cases, one can look at first order stationarity. That means I am looking at one observation at a time. I am analyzing single observation, and in this case what we are saying is when I pick a single observation, the distribution should not change with time, and when I look at second order stationarity in distribution, then I am looking at the joint distribution of two observations, and that should remain invariant with time. And now you can go on, you can say that the joint distribution of three observations should remain invariant with time and so on. As the strict stationarity consumes or subsumes all order stationarities. Remember, it says that it should be stationary for all sample sizes. Again, these are all idealizations that are important, but there is a particular point about the second order stationarity in distribution. When we require that the joint PDF of two observations remain invariant with time, it also implies that the distribution is only a function of the time difference that you are looking at rather than the time instants, because it should be independent of time. So, the only way this distribution can be different is when you are looking at, for example, observations x1 and x2 and x1 and x3. Obviously, this statement does not require that the joint distribution of f of x1 x2 should be equal to f of x1 comma x3. This is not necessary. What it says is instead this can be equal to, this should be equal to what? Some other f of x5 comma x6 or x4, does not matter, right. Two successive observations should have the same joint PDF. It does not matter where those two successive observations are located in time. It could be now, it could be later, or it could be even more later, does not matter. Any two successive observations I pick, or any two observations that are separated in time by k2 minus k1 should have the same joint PDF. This is a stronger requirement than the first order stationarity. Is it clear? This is important to understand, because very soon we will talk about what is known as a second order stationarity in moments, or wide sense stationarity or weak stationarity. There are different names to the same thing, which will have this kind of a property. but in moments only. Here we are saying distribution should remain invariant with time as long as the observations are separated by a certain time, time difference, or what we call as lag. When we move on to White's and stationarity, we will require that the moments remain invariant with time and they be only a function of the time difference. We know that moments are subsets, they are being generated from the distribution. So, distribution is the Pitamaha, moments are all children of the distribution. So, here we are saying the parent should be invariant. Okay. So, even to verify, to satisfy the distributions to remain invariant with time like this here is quite difficult. It's in fact, it's quite unrealistic to expect. Now, again we ask here this question whether this is necessary. Remember, we asked a similar question in predictions. What was the question that we raised at that instant when we talked about predictions? We said conditional expectation is the best prediction. But then we realize that conditional expectations are hard to compute because they require the knowledge of joint PDFs, correct? And then we asked, well, conditional expectation is a nonlinear function of the predictor or the regressor. Do I need such a nonlinear function? Can I work with linear functions? And then we had some discussion saying, yeah, in practice I would like to test the use of linear predictors. If they do a good job, then it is great, correct. If they do not, then we will worry about nonlinear predictors and so on. Likewise here, maybe I do not need this strict stationarity, even I do not need perhaps the second order stationarity, forget about strict stationarity, I probably do not need the second order stationarity in distribution. I can focus rather on moments, and that is what the relaxation that generally one looks at. The question is, what is that relaxation exactly, and when is that relaxation justified? When can I work with a relaxed sense of stationarity, right? All of this is to make sure, remember, every time you have to ask yourself, why on earth we are having this discussion? Because we want to make sure that the models that we work with or the inferences that we draw, it need not be models alone. It can be features, it can be whatever classifiers that you have developed on a single realization should work for future as well and should work in the past as well. That is the reason why we are talking all of this.